All right, so my name is Daan Beelen. I'm with the Sand Consortium at the Colorado School of Mines. And my presentation is about why I think smaller bed forms tend to outpace bigger bed forms. So this has kind of been my COVID lockdown project because it was kind of difficult to do field work and lab work. So I decided to do this, which basically just involves satellite data. And I think the results are actually really interesting, but some of it's kind of complicated. So I'm inevitably going to have to gloss over some kind of important details, but I hope that people can still follow the main ideas. So why are dunes important? Well, basically, dunes are a major constituent of any kind of sedimentary record, whether it's aeolian or fluvial or abyssal or tidal. It's very common for the sedimentary record to be comprised of stacked dunes. So kind of figuring out the physics behind them will give you a lot of insight into how these successions can form and why they look the way they look. And also it's, as you can see, that some of this information can give you a direct prediction of how fast a dune is moving. So that's kind of interesting. And in the last slide, I'm going to try to convince everyone that a single picture, like the one you see in the bottom right now, is enough information to determine how fast that actual dune will be moving. So this is an example of some tidal dunes that are stacked. So it doesn't matter if it's tidal or aeolian or whatever, it's all going to be stacked dunes, right? The main concept that I'm going to talk about is surface to volume ratio. So it turns out that if an object increases in size, its amount of surface area compared to volume decreases. So for example, you see a cube in this slide. This cube, the cube on the left, the small one, has length 1, and it has a cube has 6 sides, so it has a surface area of 6 and a volume of 1. So its surface to volume ratio is 6. If you double the size of that dune, the length becomes 2, the surface area becomes 24, the volume becomes 8. So the surface to volume ratio is only half the amount of the surface to volume of the small dune. So the reason this is relevant for dunes is because the only sediment that is available for transportation is the sediment that sits at the surface. So a bigger dune, which has less surface area compared to its volume, will have less sediment that sits at the surface that is actually able to be transported. So the hypothesis is that larger dunes have a lower surface to volume ratio and therefore a lower migration rate. The methodology is quite simple. It basically just involves sequential time-stamped satellite pictures. So here you see an example of a dune field, a barchan dune field in Morocco. So this particular satellite photo was taken in 2017. This one was taken roughly 1 year later. So you can see that they've moved quite a bit in that 1 year. And because all of this is geospatially referenced, it's quite easy to do measure the sizes of these dunes, and based on the displacement across time, you can calculate how fast they're moving, right? So this is kind of what the data looks like. This is just a plot that has the surface area on the x-axis and the corresponding migration rate for all these dunes on the y-axis. The dune field we just looked at in the previous slide is shown here in the red dots. It's in Morocco. And in addition to that, there's a bunch of other dune fields. Now, what you'll see is that in every case, the smaller dunes within a dune field travel exponentially faster than the larger dunes. And the trend lines that define these relationships are located here in this gray box. And they each have their unique base number. So each trend line is a parabolic trend line. And in each case, there is a unique base number to this parabola. So for white sands is 0.7, but the exponent is always the same. So it doesn't matter where you are, it doesn't matter whether you're in white sands or Peru or Morocco or China, the exponent is always minus a half. And I'll explain later why this is and how it's related to the surface to volume ratio. So in order to kind of prove the hypothesis, I needed to figure out the surface to volume ratio. So in order to do that, you need both surface area and volume. So obviously surface area is relatively easy to measure from satellite data, but volume is a little bit more difficult. So in order to figure that out, I built a 3D model of a dune with the assumption that this forward-facing lee face sits at a constant angle of repose of 34 degrees, which, because most Aeolian dunes are sand, you can kind of assume that this forward-facing lee face is always 34 degrees. So based on that assumption, you can resolve the entire three-dimensional volume of this dune. So, and after I built this model, I imported it into SketchUp and basically figured out a relationship that you can use that can link the surface area that you measure to the volume that you'd expect. So then you can have the surface area and a volume measurement, and by dividing those, you can get the surface to volume ratio. So this is basically the same slide as we saw earlier with the same 6 data sets. And instead of having surface area on the x-axis, we now have surface to volume ratio on the x-axis. And you can clearly see that there's a universal linear correlation between the surface to volume ratio and the corresponding migration rate. So this proves that the surface to volume ratio is a major control on the speed of this dune. And this is related to the fact that more surface area gives you a higher proportion of sand that is affected by the wind, right? So it has been recognized previously that for Aeolian dunes, the migration rate is proportional to 1 divided by the height of the dune. So I'm not saying that this is wrong. In fact, my data corroborates that this is correct. But I'm saying it's kind of wrong, right for the wrong reasons, because basically the reason this is linearly proportional to the migration rate is because it has the same unit as surface to volume ratio. 1 over height itself doesn't really have any physical meaning, but surface to volume is an important parameter because it controls the amount of surface area that's available for movement. And another, basically every parameter that is related to the size of the dune that has the unit of m to the power -1 will have a linear relationship with the migration rate. So you don't necessarily need 1 over height. You can use 1 over length, 1 over width, 1 over any one-dimensional parameter that's related to the dune has the same unit as surface to volume ratio. So it will have a linear relationship with the migration rate. Now, the reason we saw earlier that if you correlate migration rate with surface area, that the exponent is always -1/2 is because surface area does not have the unit of m to the power -1. It has the unit of m squared, right? So in order to kind of convert that into the correct unit of meter to the power -1, you don't need surface area by itself, but you need 1 over the square root of the surface area, or in other words, the surface area to the power -1/2. So that's why all these trend lines have this same exponent, because in the end, everything is related to surface to volume ratio. That's the thing that really controls the speed of the dune. So this is an example of a data set in Yemen. So these are 10 dunes, and here's 1 over the height of the dune, which is a linear relationship with the migration rate. 1 over the length has also a linear relationship. 1 over the circumference, or 1 over the perimeter. All these, 1 over every one-dimensional parameter will have a linear correlation with the migration rate. And the reason, of course, is that surface to volume ratio is controlling that. So obviously, surface to volume ratio is not the only thing that's controlling the speeds of these dunes. There are also environmental factors like wind speed or those kinds of things. And those are all encompassed by this parameter that I call the scale adjusted migration rate. Now, the way that you can calculate that is simply to normalize the dunes within a dune field or variations in size. So what you do is you divide the speed of the dune by its corresponding surface to volume ratio. And by doing that, you can see that this value, scale adjusted migration rate, or B, is basically the same for every dune within a dune field, but it's widely different from dune field to dune field. And it corresponds basically to all environmental parameters that affect the motion of this dune. So this is a compilation of all the data sets that I measured. There's 12 in total. 10 of them are Aeolian dune fields on Earth. One of them is on Mars. Another one is the Florida data set, which is underwater. It's a tidal barchan dune field. And they all have their own unique value for scale adjusted migration rate. Like Mars has the lowest one, the highest one is in the Namib Desert. And one thing that's very interesting is that these insights into surface to volume ratio can also give you an idea of not just the scale dependent migration rate, but also the scale independent migration rate. And I'll kind of try to explain how that works. So surface to volume ratio is kind of like temperature. It's not really, it's like every object has its unique surface to volume ratio, but different portions of this object can have a different surface to volume ratio. So for a dune, the base of the dune has the lowest surface to volume ratio, and there will always be a progressive development from the base to the top of low surface to volume ratio to higher surface to volume ratio. Now, this by itself is not particularly special, but because the movement of this dune is also controlled by environmental factors, the way that the surface to volume ratio is translated into the speed of the dune is portrayed by the shape of the dune. So the speed of the dune is the lowest at its base, and it increases progressively towards the top. Eventually, the speed reaches a point where it's too high for the sediment to be contained within the dune. So I call that the critical velocity. And the distance across which this critical velocity is reached is shorter for areas that have a high scale adjusted migration rate. So the ratio of the backwards facing stoss side and the forward facing lee face is an indication of the environmental parameters or the scale adjusted migration rate of that dune. Right, so if you measure these two, the stoss and the lee, the length, then the ratio between those can give you the value for B. So this is a compilation of all the data that has scale adjusted migration rate on the x-axis and the ratio of lee versus stoss on the y-axis. Because there's like a lot of data points, I turned this into a density scatter plot, and the blue dots are data set averages. So the relationship between these two is quite good, and that's really exciting because by exploiting that ratio, you can not only figure out the size of the dune, but you can also figure out the environment of the dune. So how fast the wind is blowing, essentially. That is all encompassed within this value for B. So if you combine these two equations, so first the migration rate is the scale adjusted migration rate times the surface to volume ratio, and then the scale adjusted migration rate is related to the ratio of lee over stoss, then you can combine that into a single equation that should be able to universally predict the speed of any dune, right? So this is kind of the effectiveness of that prediction. On the x-axis, you see the equation that would universally predict all these migration rates, and on the y-axis, you see the corresponding measured velocities. So you can see that it doesn't really matter where you are, even dunes on Mars can be predicted using this one equation. B and C basically show the same the same data. In B, you see a histogram of the measured versus predicted migration rates, and in C, you see some scatter plots of these things. And you can see that it doesn't really matter which location you are, whether you're in Morocco or Egypt or White Sands or wherever. The universal equation is always effective at predicting the speed of these dunes. So yeah, that's the end. Does anyone have any questions?
All right, yeah. I think actually I think my colleague Rebecca has a question for you.
Okay.
I have questions, and I'm technologically challenged apparently, and I was messing up trying to submit my questions to the chat, so I apologize, everyone. I can't, okay, all right, it looks like somebody fixed it for me. Okay, thank you. So I did have a couple of questions. I do not want to take up time compared to any of our attendees. So attendees, please submit your questions and raise your hand if you have some. And I apologize, Don, in case my questions were answered by your talk while I was busy trying to figure out how to fix my technological difficulties. But I wanted to ask about, did you, oh, right, I recall now. I saw that you mostly just used barchan dunes, or I think only used barchan dunes in your analysis. Have you tested these relationships on parabolics or transverse or any other sorts of dunes? I know, for example, at White Sands that the parabolics move much more slowly than the barchans, if I recall correctly. And I was just wondering if that is that because of their surface to volume ratio that you talked about, or is it because parabolics have I mean, I know they have some differences to barchans, but is it what you found, or is it a different difference, if you will, or do you know?
So that is a really excellent question. And if I would have more time than 15 minutes, then I would probably spend a lot of time talking about that, because I measured every morphology that there is in White Sands. And you see that if when these dunes start amalgamating, so for example, from barchans into transverse dunes into amalgamated barchanoid dunes, their surface area decreases again.
Yeah.
So correspondingly, the migration rate reduces. And I think there's actually more to this. I think it's actually a more intimate link, because you see that they're responding heavily to topography as well. You can see that when the dunes migrate upwards, the decrease in velocity could actually be forcing them to, because they're moving upwards, forcing them to amalgamate to reduce their surface to volume ratio. Now, parabolic dunes are kind of a different story. So parabolic dunes, they have an opposite relationship. So larger parabolic dunes actually move faster than smaller parabolic dunes. And that's because parabolic dunes are not controlled by their exposure to the wind. They're controlled by the degree of fixation, mostly by vegetation.
Right, holding their arms down.
Yeah, so parabolic dunes, you're right, they're the slowest moving morphology. And they actually have an opposite trend with regards to size and migration rate. And that's related to, that's also the reason why they have this opposite shape. But yeah, you can probably tell I can talk about this for like another hour, but I don't think that's the point here.
But do you think it's the chicken or the egg?
Well, that's the thing.
Are the parabolics slowed down by the vegetation, or can the vegetation grow because the parabolics move more slowly than the barchans?
No. The parabolic dunes slow down because of the vegetation. So there's a point where the water table is high enough for lots of plants to grow, and in that region, the plants start to fixate the sediment, and they preferentially or more easily fixate the smaller parabolic dunes, and that causes them to slow down a lot. And the ones that are larger, they manage to be a little bit more free, so they can actually move faster than the smaller parabolic dunes.
Very cool. Thank you.
All right.
I know someone else had another question.
Yes, but we are kind of butting up right to when Natalie's talk should begin.
If Norman has a quick question, I will personally take the guilt of making it run over. Since I asked the first question, I'd like to go ahead and let someone else ask one.
I will unmute Norman then.
Very quick. First of all, I think your methodology is very clever. Well done. The only question I would have for you is that it looks like that the mineral doesn't matter what the minerals are, whether it's quartz or anhydrite or silica sand or carbonate. Is that correct? Because they all have different specific gravity, and I would assume that they have a different rate of motion for any given wind. But as I look at your chart, looks like it's totally independent upon specific gravity.
So it's probably not totally independent. It's probably the mineral density is probably something that is encompassed within this B parameter, the scale adjusted migration rate parameter. So for example, for the case of white sands, you'd have a low scale adjusted migration rate. That's partially because it's anhydrite, but also perhaps the wind is not blowing very fast, right? So all of those environmental parameters are all encompassed by this value for B.
Okay, okay. Yeah, I wondered about whether that would account for it. Thank you. Well done.
Thank you.